Hello dear student, welcome on this video lecture, and we will start this video lecture with example. Example is let A vector is given as 2 I cap minus 4 j cap plus k cap, and B vector is given as I cap plus 3 j cap minus 2 k cap. We need to find A cross B. So basically we have picked this example for cross product, and in the previous video we have learned what the cross product is. Before we start solving this, let's say recap about the last lecture and particularly this cross product. So two vectors can also be multiplied in cross fashion, which is called cross product or vector product. It has been defined as magnitude of first, magnitude of second into sine of the angle between the two vectors and the direction n cap. AB sine theta is the magnitude, n cap is the direction. That's what you have learned, and you have understood what the direction of this A cross B is. Direction of A cross B is perpendicular to A as well as perpendicular to B. That means it is perpendicular to the plane in which A vector and B vector lies. Moreover, it follows the right hand rule. And then we have talked about certain properties of A cross B and I cap, J cap, and we have also understood how to find this A cross B as a determinant method and or otherwise method. So we can find A cross B if it is given to us. And properties we recall, so A cross B is not equal to B cross A, it's rather equal to minus B cross A. So that means direction of A cross B and direction of B cross A are exactly opposite to each other. And we have also understood that if the cross product of two vectors is 0 and the vectors are non-zero, then we can claim out of it that A vector is parallel to B vector, or you can call them collinear, and that can be claimed in both ways. If they are parallel, then the cross product is 0. This arrow means, both side arrow means this implies this and this implies that. So if A cross B is 0 and A and B are non-zero vectors, then they must be parallel. If they are parallel, then this must be 0. The cross product must be 0, right? And we have talked about the maximum value is A, B and all other stuffs. So this is what it is. Now what the determinant method is we are going to use in this particular example. So let's use this. So A cross B we need to find out. So A cross B is going to be equal to, for that sake we are going to draw a determinant. That means we will be having two parallel lines and we will be writing the rows and columns within those lines, and then we will be expanding it to find out the final expression of A cross B. Now how we write this? So we have understood, we write I cap, J cap, K cap in the first row. In the second row we write the coefficient of first vector, which is A vector, which is having coefficients or components 2, minus 4 and 1. So we write it as 2, minus 4 and 1. And then last row, which is the third row, we write the coefficient or components of the second vector, corresponding components. I is 1, J component is 3, and K coefficient or component is minus 2. Then we have to learn how to expand it. So we will be writing this I cap and writing the coefficient of it or component what is coming with this. So this I cap, for that sake this column will not be considered, this row will not be considered, this is small portion will be considered. We will multiplying this in a cross fashion. So minus 4 and minus 2 will get multiplied to make it, I'm writing directly 4 into 2, that is 8. Then minus, we place a minus, then we multiply this in a cross fashion, 3 into 1, that becomes 3. So this will become the coefficient of I cap. Once we have written I cap, then J cap is coming, this J cap has to be written with a minus sign, and then we need to perform the same operation. The column will not be considered, the row will not be considered. So 2, 1, 1, minus 2 will be making it. Then 2 and minus 2, they will get multiplied to deliver as minus 4. So we write it as a minus 4, then minus 1 and 1 get multiplied to get 1. So 1 and 1 is 1. And finally we will be writing this K cap, doing the same stuff. So the first row will not be considered, the third column will not be considered. 2 and 3, they will get multiplied to 6, minus the 1 and minus 4 will get multiplied to minus 4. So this will be minus 4. So that's a minus 4. Now we can simplify further this. So this becomes 8 minus 3, that's 5 I cap, and minus 4 minus 1 is minus 5 and minus outside, so that's 5 j cap, and this is 6 minus of minus 4, that's a 6 plus 4, that is 10 k cap. So if we want, we can write this a cross b. A cross b is equal to, we can take this 5 outside as a common, so it will become I cap plus j cap plus 2k cap. Now if somebody asks find the magnitude of this a cross b, we can find the magnitude of this vector by doing the squaring and under root adding them within that square root, right? And this is a cross b, so this is how we can find the cross product of two vectors. If the vectors are given to us, we will make the determinant, we can expand it to get a final answer. Suppose somebody is asking in this question find b cross a, so we can find this b cross a directly. Either we can make another determinant and expand, or we can say it's going to be minus a cross b, and since a cross b we have calculated, so we can say our answer is going to be minus 5 I cap plus j cap plus 2k cap in that bracket. And you can check the magnitude of a cross b and magnitude of b cross is going to be equal, because this minus sign will not matter. We know the magnitude of vector is a positive quantity, right? So this is an example how to use the determinant to get the cross product between two given vectors. Now let's move ahead. Let's take one more example, and this example is particularly making us comfortable about the use of the direction, or we will be learning how the directions will be used. So sometimes you might be asked like this questions, east direction and north direction, when the directions are multiplied, what they deliver. And so north dot east or east dot north, then west dot east, and cross. So dot and cross have been asked in a couple of questions. We need to find what their values are going to be. So let me first explain what the directions are. Generally we draw the direction like this. This direction we say this, let me make it proper, one in this direction, and another maybe this direction. So if we show this kind of direction in two-dimensional plane, then we call this as a east. This is denoted to north. If east is fixed, so all of will be fixing, because opposite to east is a west, and then there will be north in anti-clockwise sense, and the south will be opposite to north. Now this is two-dimensional picture, mind it. That means this picture simply says we are drawing this directions in this plane, but actually this north is not vertically upward. So vertically upward is not this north, and the south is not vertically downside. If this kind of picture is shown to us, and if somebody asks what is the vertically up direction, so we will say the vertically up direction will be the direction coming out of this plane of the screen and outwards. So this outwards direction is going to be this vertically upper direction. And what is vertically down direction? That's going to be inwards. So we can say in this picture we are looking for, so we will call this direction which is coming outwards, we know this outwards, this will be upwards. Upwards means vertically upwards, or let me write simply upwards. This is three-dimensional upwards, and the inside is going to be indicating downwards. Are you understanding my point? Because this north, south, east, west, if you look in the practical consideration, then they are in the horizontal. So all are in the horizontal, and upward direction is perpendicular to the horizontal. Though this north appears to be upward, but this north is not upward in actual sense. It is horizontal. East is horizontal. So if I draw them three dimensionally, so this will be, there will be some sort of this. This might be east and west. We can call them east and west in this manner, and then there will be another directions running like this. Let me extend it a bit and take it somewhere here. They are 90 degree. So they will be north and south, and then will be another direction which will be upward and downwards. And let me join over here. So this will be actually representation in 3D. You can call this is your east, then this is your north, then this is west, this is indicating south, then this is indicating upwards, and this is going to be indicate downwards. So I have shown both the considerations of both the views. This is three-dimensional views that we experience in our practical life, and the above one is for that purpose, which is basically in two-dimensional, that we show in papers or screens, which is two-dimensional for us, right? So this thin line is dividing the two. So either a figure will be made like this or will be made like this. So we need to understand which what means this. This means like north is south, they are perpendicular to each in this way, and upwards is outwards and downwards is inwards. In this case, this is going to be 90-degree angle, this is going to be 90-degree angle. So they are in this manner, 90 degree. Okay, now we can think of what these means, these directions are going to mean for us. So east dot north, east is going to be in the direction of east, and north is going to be in the direction of north. So what the angle they are going to making, whether you look at 2D or look at 3D, angle is going to be 90 degree. So we know these are the two directions and which are in the 90 degree. It's like I cap, j cap. Making sense or not? If they are like I cap, j cap, that means their dot product is going to be 0. So we will say this answer has to be 0, because dot product of two perpendicular directions is always 0. Now second part, which says west dot east. Now west is there, east is there. What the angle they share? There is angle 180 degree. So if the two vectors are opposite in direction, and these are the directions, so they are unit vectors. So we write this dot product as a magnitude of 1, which is a unit, magnitude of second, which is unit, into cos angle between them, and angle here is 180 degree. So cos 180 degree will become our answer, which is going to be -1. So if it is being asked what is the value of west dot east, so we have defined this dot product in such a way that west dot east will be equal to -1, and east dot north will be 0, because here the theta was 90 degree and here the theta was 180 degree. Making sense? This is how the dot product is used or defined, so that we can manipulate the directions in dot fashion. Now there are three examples for a cross, so let's check what their values are going to be. We know unit vectors cross product comes out to be unit vector. That means directions when multiply in a cross manner, the answer will be direction. In the first two cases, the answer is not a direction, it's simply a magnitude. Okay, so east cross north. So when we do the cross product between east and north, what should be the answer? So it will be a perpendicular both towards both to east and north. So 3D picture will be more appropriate, or you can see the 2D, both are going to be giving the same answer. So we need to find a direction which is perpendicular to east as well as perpendicular to north. So perpendicular to east, perpendicular to north is going to be either upwards or downwards. From here it is also clear, perpendicular to the board that has been shown for this 2D figure. Now moreover, to find the correct direction, we use the right hand rule. So we place our fingers in the direction of east. So we place our finger pointing in this direction and convert curling naturally towards north. So right hand fingers, if you do place in the direction of east and curl toward the north, then thumb will be in the upward direction. So we can say this is going to give us the upward direction. Now this is just these questions are just for your practice, how we are getting the directions doing the cross product. So if we do the cross product between east and north, then it will be upwards. Now if I have written north cross east, then you will say the direction will reverse and it will go downwards. Now what the value of west cross east is going to be? So west and east cross product, they will be having an angle 180 degree because they are opposite. and we know the cross product like goes like magnitude of one, magnitude of another into sine angle between the two, which is 180, into the new direction. But we know this sine 180 will make it 0, so it will become null vector. That means east cross west or west cross east comes out to be null vector. That means it does not carry any direction, or its direction is difficult to decide, and it's having 0 magnitude. And then the final is a south cross upward. So when we do the cross product of south with this upward, so again one direction another direction, they are not parallel to each other, hence it won't be 0, so it will be another direction. Now what that direction is going to be, we can find using the direction rules. So upward is in this figure is upward is this, south is this. So product that means the product cross product of these two must be perpendicular to south as well as perpendicular to upwards. It must be in either in the eastward direction or westward direction. Then we need to place our fingers in the direction of southwards, and they have to curl towards the next vector, that is upwards. So if you place your right hand in such a way that fingers point out toward the south and then curl naturally towards upward direction, then you'll find the thumb will be running towards west, or thumb will be pointing towards west. You can do this, then you'll find this is going to be indicating the west direction. Now this particular slide is very important in order to understand how we are using the directions in dot fashion and cross fashion, particularly in cross fashion, and how we are getting the new directions when they are getting multiplied. Making sense? So just understand properly. If you have any issues, you can rewatch it, or otherwise you can ask as a doubt. Now let's move ahead and talk about applications of cross product. Just like we learned about the applications of dot product, similarly we will be learning about the application of cross product. Let me recall you, in case of dot product, the applications primarily were to find out the angle between two vectors, and we talked about projection of a vector along and perpendicular to another vector. For that purpose we use the dot product. Apart from checking the perpendicular case, here we will be talking about the application of cross product. So one is to find area of a triangle. So if a triangle is given to us, we can find the area of a triangle using the cross product. How? We are going to learn over here. So let's say we are having a vector A, that means its magnitude is A and direction is given to us, and another vector B, that means its magnitude is B and it's given to us, and let's say these two vectors are known to us. So we can join the tails of these two vectors. So if we join the tails of these two vectors, so they will become this kind of structure will become. Now this is not a triangle, but yes, this is almost can be made a triangle. For that sake, we need to simply do one thing. We need to join the head of this B with the head of A. That means to construct this triangle, what we need to do, we need to have a simply two vectors A and B. So if we have two vectors A and B such that their tails are joined, then if we just construct a line joining the two heads, that will become a triangle. Now this triangle's area can be easily identified. Now for that sake, we can think of this as point O for you can think of origin, and this point is A, that's terminal point of A, and this is point B. So here this A point is going to indicate OA vector, that means it's also position vector of point A, and this B vector is going to be indicating OB vector, which is position vector of point B. Making sense or not? Yes. So if it is making sense of what this area is going to be, now this length OA length is A, OB length is B. Now whenever we want to find or we are interested in finding the area of a triangle, so definition for to use the area or find the area, what we need to use is the perpendicular or the height. Okay, so let's drop a perpendicular, and this perpendicular is on A, and this is height. Let's call it this height to be H. Now we know the area of a triangle. What the area of a triangle is? Area of triangle. Which triangle we are looking for? We are looking for triangle OAB or AOB, whatever you name it. So this area, let's say we are indicating this area by this symbol delta. So if this is area, it's going to be half base is OA into height is h that I have written over there. Now then after this OA can be written as this OA is the magnitude of A, so vector, so it's going to be half A into h. Now what will be given to us? This position vector A and B will be given to us, so we will be rewriting this thing. Now let's say this angle is theta, so you'll find this theta is going to be angle between vectors A and B. Now let's say this foot of perpendicular was any point C, so we can say what this theta is going to be. Now if we use this sine theta in this triangle, so in this triangle, let's say we are catching triangle OC and B, and we are interested to write sine theta. So let me write over here sine theta we are using in the triangle, right angle triangle OCB. So sine theta will be saying the perpendicular divided by hypotenuse, which is OB. So from here we can catch what the h value is. Height is going to be OB length into sine theta. But we know this OB is nothing but the magnitude of vector B. So h is going to be written as B sine theta. So this is something we have used, or trigonometry that we have used to find the value of h. We can substitute the value of h over here. So the area of this triangle is going to be equal to half, that means 1 by 2 A into h. In place of h we can write this value, which becomes A into B into sine theta. Now we also know that if we go for the cross product, since we know that the magnitude of cross product of A and B is AB sine theta. AB sine theta. So if this is the magnitude, so from here we got a formula that the triangle's area is going to be equal to half times magnitude of A vector cross B vector. So point is that if we know the vector A and if we have been given the vector B, then we can go for the cross product of vector A and vector B, and then we can find the magnitude of that cross product, and we need to simply divide that magnitude by 2. That will give us the area of the triangle formed by the vector A and vector B. So this is how, by measuring or by calculating this cross product, we can find the area of any triangle which is formed by these two vectors A and B. Making sense? So that becomes an important expression to be understood and remembered. And whenever vector A is given to us, vector B is given to us, and you will be asked like area of a triangle formed by these two vectors, you simply go for the cross product, get the magnitude out of it and divide by 2. How to do this cross product, that's what we have learned, right? And how to get the magnitude of that cross product, we also know that. So we can find this, and this is going to be in proper unit, whatever the unit is given to you. Let's solve this example, and this will give us an expression as well. It says find the expression of area of given triangle. So this triangle is known to us, ABC triangle, and further things are given to us that A point has a position vector as A, B point has a position vector as B vector, C point has a position vector as a C vector. That means somewhere there will be origin, and if we join this point A from the origin, this is A vector, and if we join this with B, so this is going to be B vector. Similarly, we join with this C, so this is going to be C vector. So basically A, B, C, they are indicating the position vectors for the points A, B, C respectively. Making sense? Now for this particular thing, we need to find how this area will be expressed for this triangle. Now these are the position vectors, so what we need to know, we can use the formula that we have talked about. So solution we can write like this. We know the area of the triangle, so area of the triangle, let me write by this. This is area, indicating area. Sometimes we indicate area by this symbol. So area of a triangle ABC is half magnitude of any two vectors. So we can think of this as one vector, this is another vector. So we can take this AB vector and AC vector as our reference, and as per the formula is going to be AB vector cross AC vector. Making sense? How this is the formula that we have just derived for triangle's area. Now we will be using this and we will be simplifying this in terms of given position vectors. So this is going to be half mod AB vector. Now we know any vector can be written as a position vector of the second minus position vector of first. So AB vector can be written as a position vector of B minus position vector of A. So can we write directly it's going to be position vector of B minus position vector of A. Then there is a cross product. And then AC vector will be written as a position vector of C minus position vector of A. So position vector of C is C vector and position vector of A is A vector. So what I have done, let me make clear. I have used this formula called AB vector is written as position vector of B minus position vector of A. And this is one of the formula that we have already understood in previous videos. Now let's carry with this. So triangle's area is going to be half. Now at least we can see in our answer or expression is in terms of the given position vectors. So we can expand it. So we are going to expand it. Let's say this B goes inside, so it will be having B cross C. We know that in cross product we need to keep the orientation, or this we should not exchange the positions. So B cross C, and then we will have a minus B cross A. I'm opening by introducing this inside. Then let's say making inside, so it's going to be minus A cross C, and this minus will become plus, so plus A cross A. Then we can use the properties of cross product that we have learned. Now this half remains as such, and there is a B cross C, so let's maintain this B cross C. Now this is B cross A with a minus sign. We know A cross B is equal to minus B cross A. So if we exchange the position of A and B, then this minus sign will be absorbed. So it can be made as a plus. So plus A cross B. Similarly, this minus sign can be absorbed. So it will become plus C cross A. We are using the property of cross product that exchanging the position brings a minus sign. Now A cross A, this is a cross product of a vector by itself, so that becomes null vector. So that becomes null vector. So from here we will be having this kind of a formula, or our answer in this particular example, that the triangle's area, if the position vectors are known to us, is going to be half mod of A cross B plus B cross A, A cross B plus B cross C, B cross C the first term, plus C cross A. So that's going to be in cyclic order and doing cross product between two vectors at a time and adding rest of it. So this becomes an important formula. So area of a triangle is going to be written as a half mod of A cross B plus B cross C plus C cross A if A, B, C vectors are indicating the position vectors of vector, these vertices or terminal points or endpoints or whatever you name it, or corner points. So sometimes we will also indicate as this is A vector, that means position vector of A. This is B vector, that's position vector of B. This is C vector, that means position vector of C. Now here A vector is not this AB vector, right? And unlike the earlier case. So here these are the position vectors of the vertices. If we know the position vector of vertices, this is the area of a triangle. I hope it's making sense. You can make your notes and understand this. Next application of cross product is area of a parallelogram. So we can also find area of a parallelogram using the cross product expression. So let's say we have two vectors, A vector and this is a B vector. A vector is pointing in this direction, B vector is pointing in this direction. If we join these two head points, so this becomes a triangle because the tails are joined together. So this becomes a triangle. But we can also create a parallelogram just by using two vectors. So for that sake, what we need to do, we need to shift this or take this vector A and translocate and place over here. We know that a vector can be translocated from one location to another location without changing the magnitude as well as the direction. and at the same time we can translocate this B so that it remains B, and we can join over here. So let me join B as well, from this tail to this head to this, and we can mark this. This is going to be vector B. Now, if we do this kind of stuff, then you'll find this will be a parallelogram. That means a parallelogram can be created just by using two vectors A and B. So if this is a parallelogram, we can find the area of this parallelogram. And in simple term, if we talk about, if we join this by this as a construction, then you'll find this line will be dividing this parallelogram into two equal halves, and this will be the area of a triangle, this will be area of another triangle. If this was vector A, so this is also going to be vector A, this is going to be vector B, just like this was a vector B. So that means here the parallelogram is basically occupying the area twice of the area of a triangle. And if we can use the area of a triangle, so we can say the area of a parallelogram, this area is going to be equal to we can say area of a parallelogram. So let's say this is indicating the area of a parallelogram. This is going to be equal to 2 times area of a triangle, that we have already calculated. I am writing in short, you can make your notes proper. So this area of the parallelogram is going to be equal to 2 times, and what was the area of a triangle? It was half A cross B magnitude, where A and B used to be the vectors that were creating the triangle. Now from here we got this formula that this area of a parallelogram is equal to twice of the area of a triangle, which is going to be basically magnitude of A cross B. So that means if we have been given two vectors A and B, and somebody asks find the area of the triangle formed by these two vectors, that means the question is demanding for the area of this complete parallelogram, which is basically two equal triangles, and one triangle is half A cross B, so two triangles will together make is A cross B, and this mod of it. So that becomes another formula to find out the area of a parallelogram. Making sense? So that's another important part. If the question will come, it will be very straightforward. A vector will be known to us, B vector will be known to us in terms of I cap, J cap. Then we will find A cross B. We have learned how to find A cross B. Then we will find the magnitude of it, and that will become the area of a parallelogram. If the area of the triangle has to be calculated, place the half factor. Okay. So these are the two applications of cross product of two vectors. So with this, we have covered all the basic aspects related with the cross product. So we can find the cross product, and we can use in these two manners. Now let's cover one more point in this video lecture, and that will be all. So the next point that I wanted to cover is this Lamies Theorem for forces in equilibrium. So Lamies Theorem, there's a statement written and the condition written. Let me explain what it is. So let me first what the statement says. It says it states that if three forces, so it talks about three forces that are acting at a point and they are in equilibrium, then each force is proportional to the sine of the angle between the other two forces. So let me explain what are the terms involved means. So three forces has to be there. So let's say F1 is a one force which is acting in this direction, F2 is another force, F3 is another force, and let's say the angle between F2 vector and F3 vector is alpha. So this alpha angle is between 2 and 3. Beta is angle between F3 and F1. Gamma is the angle between F2 and F1. So these angles have been shown over there, and these three forces are in equilibrium. There's a meaning of equilibrium. Whenever it says the forces are in equilibrium, that means the resultant force is 0. So yeah, here we will find the resultant force. We know resultant force is calculated by adding all the vectors together. So it will be adding F1 vector plus F2 vector plus F3 vector. That means we are adding all the forces together. So this is vector addition of all the forces. Now this is called resultant force or net force. So when the forces are in equilibrium, then the net force is zero. That means there's no net force acting. So equilibrium means net force is zero. Now we know this f1 plus f2 plus f3, these are the three vectors, and there the sum is zero. That means if we arrange them, they will be creating some kind of triangle. So if this is f1 vector, then there will be some f2 vector existing and f3 vector existing, so that they will be nullifying each other. So if we make this f2 like this, so this is f2 vector, and then this is going to be f3 vector. That means it will be joining this tail to this side. Now alpha is the angle between vectors. These are going to be straight line. Okay, let me show by straight line so that it appears proper. So this will be joining like this. So this will become f3. Making sense? So that's f3. So three vectors, we know if they are in cyclic order and making a triangle, their sum is zero. So this f1 plus f2 plus f3 is 0, indicates they must align like this. Now as per the angles, let's talk about the angles. So f1 and f2, they makes angle gamma. So that means this angle, let me draw by different colors. So this angle is gamma. That means between f1 and f3. f2 and f3, they have alpha. So we know if we produce this forward in this manner, then this angle is going to be known as alpha. And between f3 and f1 is beta. So we can produce this in the forward direction, and this is going to be beta. Now the same picture can be redrawn in this manner that have been shown over here. If we show all the forces co-initial, that means joining all the tails together, then f1 will be looking like this, f2 will be looking like this, and f3 is going to be look like this. And then this angle alpha will be between f2 and f3. So that means this picture that has been shown over here and this picture, they are the same pictures, right? And what the Lamies says, if these forces are in equilibrium, that means this kind of forces are shown to us and they are in equilibrium, then this is the result that holds good. This is the result that holds good. So that is a formula we can remember, and the formula says the forces is proportional to the sine value of the angle between the other two forces. That means f1 will be proportional to sine alpha, f2 will be proportional to sine beta, f3 will be proportional to sine gamma. So when we say proportional to, that means basically this is going to be of this sort. f1 will be equal to some k times, k for constant, sine alpha. So from here we can calculate this f1 by sine alpha, f1 by sine alpha, this is going to be a constant number k. Similarly, f2 will be equal to constant times sine beta, because it's going to be proportional to sine of beta. So from here we will find f2 upon sine beta is equal to k. And similarly we can say f3 is going to be proportional to sine gamma. Now we are removing the proportionality symbol and introduce this k as a constant. So from here we can say this f3 divided by sine gamma, this is going to be equal to k. Now if we combine all these three equations together, so this will be give us this equation. So from here we can find out this result. That means we can claim f1 upon sine alpha is equal to f2 upon sine beta is equal to f3 upon sine gamma. Making sense? So this is going to be Lamies theorem. So this is called Lamies theorem. So Lamies theorem is for equilibrium cases. The three forces has to be there. They should be in equilibrium. And if this is the case, then f1 divided by sine alpha is equal to f2 divided by sine beta is equal to f3 divided by sine gamma, where alpha, beta, gamma, they are the angles that have been shown over here. Now if we want to know the proof of this, its proof is quite easier, and that is basically related to some trigonometry stuff. So since we have talked about these angles, so let me quickly explain that proof. Most of you can catch that. If you can catch it, it's done. So this angle is alpha, as we have talked about. So what this angle is going to be, the angle within the triangle. So this angle is going to be 180 minus alpha. That means we can call it as a pi minus alpha. Similarly, this angle of the triangle is going to be pi minus gamma. This angle of the triangle is going to be pi minus beta. Now in a triangle there is a property, or there is a rule called sine rule. You must be learning it if you have not learned by now. Sine rule of a triangle. Sine rule of a triangle. It says the ratio of side and the corresponding angle is constant for all the sides. So this side is f1 and its opposite angle is pi minus alpha. So we can say f1 divided by sine pi minus alpha is going to be equal to f2 side and the opposite angle, which is pi minus beta. So f2 divided by sine pi minus beta. And finally f3 and opposite angle pi minus gamma, so it's going to be f3 divided by sine pi minus gamma. So this is standard sine rule in trigonometry. You will be learning a sine rule, and there will be similarly a cos rule or cosine rule. So we use this sine rule, then we will be finding f1 upon sine pi minus alpha, f2 upon sine pi minus beta, f3 upon sine pi minus gamma. We also know sine pi minus theta basically is sine theta. So that means all these terms will be equal to, they will get converted into alpha, beta, gamma. So that means it will become f1 upon sine alpha is equal to f2 upon sine beta is equal to f3 upon sine gamma, which basically becomes this Lami's theorem. So Lami's theorem basically uses the sine rule of trigonometry and also uses this equilibrium condition and gives us f1 upon sine alpha is equal to f2 upon sine beta is equal to f3 upon sine gamma. So what it is going to be the case, you will be given f1, f2, f3, you will be given alpha, beta, gamma. Out of these 6, 1 will be unknown, so you or 2 will be unknown. You can solve them and find the 2 values. Making sense? So if this kind of picture is given to us and equilibrium word is used, then you can use this as a result or equation or formula, whatever you call it. And how it is coming? Using the sine rule. Fine. So that's all for this particular video. And in this video we have covered application of cross product, and we have talked about some example of cross product, as well as this Lami's theorem for forces in equilibrium case. Fine. So that's all. Thank you for watching. Have a great time.